Welcome to This Explainer. Okay, today we're putting on our detective hats to troubleshoot a really specific, absolutely critical issue on the Teledyne T300 carbon monoxide analyzer, the dreaded temperature alarms.
Do you ever look at your reporting data and just think, why? Why is my T300 suddenly flagging invalid data out of nowhere? Why is it triggering unexpected system resets? Well, if you're seeing zero and span calibration drifts that cause these resets, the culprit is usually staring you right in the face. It's a temperature control failure. These machines are incredibly sensitive, and the second that internal climate gets thrown off, your data quality completely tanks.
So here's our game plan for today. We'll look at the temperature alarm trigger, why the T300 actually needs heat, and then we'll diagnose both box temp and bench temp alarms before finally restoring that calibration and data.
All right, part one, the temperature alarm trigger.
Let's look at the immediate symptoms and, the actual stakes of ignoring a temperature fluctuation. It's a really stark contrast. On one hand, a stable temperature means reliable data, numbers you can actually trust and take to the bank. But once that internal temp drifts, your zero and span calibration immediately goes completely off the rails. It often leads directly to a system reset or those super frustrating invalid data flags. Your data stream literally just crashes. Moving on to part two, why the T300 needs heat. Look, before we start tearing into the chassis, we've got to understand the physics here. Why does temperature even matter for measuring CO? Well, the heart of the T300 is the bench. It's this 14-meter folded optical path inside the analyzer where the sample gas absorbs infrared radiation. And man, that IR source and detector are incredibly sensitive to ambient changes. Why? Because gas temperature dictates gas density, and density changes how much light gets absorbed. It's kind of like baking a delicate souffle, right? One little draft and the whole thing collapses. If the temp fluctuates, your measurement is completely compromised. So, the golden rule here, this optical bench has to be uniformly heated to exactly 48 degrees Celsius. No exceptions. It's deliberately set 8 degrees above the maximum suggested ambient operating temperature, and it's maintained by a strip heater slapped right on the underside of the chamber housing.
Meanwhile, right next door, you've got the gas filter correlation wheel, or the GFC wheel. This thing needs to run even hotter, 68 degrees Celsius. That's about the temperature of a first cup of coffee. Now, you might be wondering, why on earth does it need to be so hot? It's to offset the intense heat radiating from the IR source itself. There's a cartridge heater implanted right into the motor's heatsink to keep it locked at exactly 68.
Okay, part three, diagnosing box temp alarms.
Let's start macro and look at the physical environment. Step one, check your rack. If your analyzer is just shoved in a power plant rack with lousy ventilation, ambient heat is going to completely overwhelm the unit. Step two, double-check that airflow. Make sure the areas to the side and rear of the instrument actually have room to breathe. And step three, check the internal cooling fan in the power supply module. Honestly, if that fan dies, your box temp is guaranteed to drift out of range.
All right, part four, diagnosing bench temp alarms. So let's say your external airflow is totally fine, filters are clean, fan is spinning, but that bench temp alarm is still screaming at you. Now we've got to go micro. We're looking at three main internal suspects here that cause bench or wheel failures: faulty heater elements, failed relays, specifically K1 or K2, or drifting thermistor sensors that are basically lying to the machine about how hot it is. First up, testing those sensors. Grab your multimeter, unplug the connector labeled bench or wheel on the board, and see if your thermistor resistance matches the factory specs. These are negative coefficient thermistors, meaning as the heat goes up, the resistance drops. At room temp, the bench thermistor should read around 30K ohms, dropping to about 11K at its 48 degrees set point. The wheel thermistor, that starts at 25K and drops to roughly 5.7K at 68 degrees. If you're reading a wide open or short circuit, boom, your sensor is dead. Replace it. If the thermistors check out, we move to the heaters. Grab that multimeter again and measure resistance on the white 5-pin connector right below the sample temp sensor on the bench. To see if the bench heaters are shorted or snapped open, measure across pins 2 and 4. You want about 76 ohms there. Across pins 3 and 4, you're looking for roughly 330 ohms. For the wheel heater, check pins 1 and 4. That should be right around 275 ohms. If your readings are wildly off from these numbers, the heater element is definitely your culprit. Now, if the sensors and heaters are both totally fine, the brain telling them to turn on is probably broken. We need to verify the relays on the relay board. K2 controls the bench, and K1 controls the wheel.
Check for a voltage change across pins 2 and 4 or 3 and 4. If the system is trying to heat and there's absolutely zero voltage change, your relay is toast. But hey, the good news is relay K2 is socketed, so it's a super easy immediate replacement.
Finally, part 5, restoring calibration and data. So you played detective, found the bad part, maybe a blown relay or a dead thermistor, and swapped it out. But we're not quite done. The T300 has a memory, right? It remembers that things went wrong. So even after you do the physical repairs and temps stabilize back at 48 and 68 degrees, those warnings will stick around. You absolutely have to perform a successful zero and span calibration to lock the bench back into its operational baseline. That will automatically clear those lingering warnings right off the front panel.
As the Teledyne manual pretty sternly reminds us, temperatures outside of the specified range or oscillating temperatures are cause for concern. Honestly, keeping a close eye on your diagnostic test functions, especially Bench Temp and Box Temp, is literally the best way to catch hardware failures before they completely wreck your reporting data. Monitor your stability.
By respecting the physics of the optical bench and methodically hunting down the exact electrical or environmental failure, you've completely conquered this alarm. Your data is rock solid again. But it kind of makes you wonder, if one tiny failing fan can corrupt a whole day's worth of data, what other silent maintenance issues are hiding in your rack right now? Keep your instruments clean, keep them cool, and keep learning. Thanks for hanging out with me for this explainer, and I'll catch you on the next deep dive.